In this video, you will learn how to conduct a two-way within-subjects ANOVA in SPSS and explore any significant effects with post-hoc tests or simple effects analysis. A two-way within-subjects ANOVA is probably the best choice if you have two independent variables with two or more levels. Both of the variables are within subjects. You want to know how the combination of variables affects the same participants. The dependent variable is an interval or ratio measurement. The data should also meet parametric assumptions such as normality, no influential outliers, and sphericity if applicable. For this example, we are going to use data from Watson et al. They studied attention capture in visual search and working memory. They wanted to know whether the combination of resource-dependent control processes and reward affected attention capture. Participants completed a visual search task while their eye movements were measured. The task included 6 shapes, one of which was the target, shaped as a diamond. The participants had to look at the diamond and ignore the other shapes. Depending on the condition, one of these other shapes was either blue for high reward, orange for low reward, or grey for no reward. In addition, working memory was manipulated by presenting participants with either 5 numbers for high memory load or 1 number for low memory load. After completing the visual search task, the participant had to recall one of the numbers. This means we have 2 independent variables, working memory with 2 levels, high and low, and distractor with 3 levels, high reward, low reward, and no distractor. The dependent variable was the proportion of emission trials where the participant's gaze looked at the distractor instead of a target. A value of 0 means a participant looked at the distractor on 0% of the trials, and a value of 1 means 100% of the trials. In the following screencast, you will see how to conduct a two-way within subjects ANOVA in SPSS using this data. For this analysis, we need 6 columns of data. As we have a fully within subjects design, each participant is contributing 1 score for each condition. This provides 6 values per participant as we have each combination of the 2 independent variables. Our columns of interest are the final 6 in the dataset. We can see they have a label for each combination, such as low working memory, high reward. The first step is to explore parametric assumptions. We can explore most of the assumption using analyze, descriptive statistics, and explore. Drag all 6 conditions into the dependent list and click on the plots option. Untick stem and leaf and tick normality plots with tests. We can simplify the box plot by plotting all 6 conditions on the same graph by ticking dependents together. If we kept it as factor levels together, we would get 1 box plot per condition. Click Continue and OK to receive the output. You'll receive a range of descriptive statistics and your plots for assessing normality. The first key output is the QQ plots for each condition. We'll break down the output later in the video, but for now, all the dots fall tightly around the line, apart from 1 value in the low working memory, no distractor condition. This value is quite far away from the other dots in the line. You can ignore the detrended QQ plots below, as it shows the same information just in a different way. Scrolling down, you'll see a box plot containing all 6 conditions. The boxes mostly look nice and symmetrical, apart from the 2 no distractor conditions. There are some potential outliers in each of these conditions, but there is one point we are going to explore closer. Case number 13 is beyond 3 times the interquartile range, so it would give us cause for concern. To explore it further, we can double check using standardized values. To create and code standardized values, click Analyze, Descriptive Statistics, and Descriptives. We can just focus on the low working memory no distractor condition, so drag this variable to the variable box, tick Save Standardized Values as Variables, and press OK. This will have created a new variable in your dataset. To make it easier to code, click Transform and Compute Variable. We're going to convert the variable to absolute values, meaning we make all the values positive. Provide it an informative name like absolute z and the condition. Click All on the function group and double-click ABS. This is a function to take the absolute value. Double-click on the z-score variable you created to insert it in the brackets. Click OK, and it will become another variable in your dataset. The final step is to code these values to what we'd expect under a normal distribution for standardized units. Click Transform and recode into different variables. Drag the new absolute z-score variable into the middle and provide it a name like outliers lone node distractor. Click Change, then old and new values. We will create 4 groups: extreme, probable, potential, and normal. Enter 3.29 in the range value through highest box and a new value of 1. Click Add. Then add a second variable of 2.58 with a value of 2. Click Add. 1.96 and a value of 3. And now range lowest through value 1.95 with a value of 4 and add. This will create 4 groups to categorize our potential outliers. Click Continue and OK, and you'll have a new variable in your dataset. To add labels, click on the variable view and values. Enter 1 as extreme, 2 as probable, 3 as potential, and 4 as normal. Click OK. Returning to data view, we can see case 13 highlighted as an extreme outlier 4.1 standard deviations away, with all the other values as normal. This might seem time consuming for one value, but you'd be able to look at the frequencies of each character with a much bigger data set. To remove this case from the analysis, click Data and select Cases. Select if condition is satisfied, double-click on your outlier categories and type greater than 1. This will only include cases with a code of 2 or more, excluding our extreme value of 1. Click Continue and OK to exclude the case. Now we are happy with the assumptions, it's time to conduct the two-way within subject ANOVA. Click Analyze, General Linear Model, and Repeated Measures. The first step is defining what our independent variables are and how many levels they have. Enter something like memory load with 2 levels and distractor with 3 levels. Click Define. Be careful here, as you have to pay attention to how you're entering the conditions. We just defined 2 variables, one with 2 levels and one with 3 levels. This has populated the within subjects box with 6 conditions. The first number is the level of memory load, and the second number is the level of distractor. It does not matter which order you put the variables in, but they need to be consistent and match these numbers. We can insert these in the order they are in the dataset. The first number will be low working memory for the 1s, and high working memory for the 2s. The second number will be entered as 1 for high reward, 2 for low reward, and 3 for no distractor. To create a graph of results, click on Plots, drag memory load to the horizontal axis and distractor to separate lines, click Add, and tick to include error bars. If you click Continue and go to the Options menu, select Descriptive Statistic and Estimates of Effect Size. Click Continue. If you want to calculate post hoc tests or contrast for the main effects, you can use those menus, but for now, we'll just calculate the main ANOVA to see where we need to focus the pairwise comparisons. Click OK to produce the output. The first key part of the output is a list of the independent variables and the variables you entered. This is useful for double checking you entered the variables in the right order. We then have our descriptive statistics. There is a table for multivariate tests, but you can ignore this. It's not relevant to a two-way ANOVA. We have Mauchly's test for sphericity. This is a parametric assumption specific to within subjects' designs. And finally, we have the main ANOVA table called Tests of Within Subjects Effects. Scrolling all the way down to the bottom, there is the graph we created to visualize the results. Just note, as standard, the axis and legend labels are not very informative, so you need to edit this. We'll now break down the key parts of the output before we return to the screencast for simple effects analysis. To break down the output you received in SPSS, there are two key elements to first check parametric assumptions. The first is normality, which can be assessed using the QQ plot. As we have 6 unique conditions, we need to look at all 6 plots. This shows the residuals cluster along the line for most of the plots, but there is one point on the low working memory no distractor condition we will explore further. The second element is the presence of any potential outliers. Here we can see the same point highlighted as in the QQ plot for the low working memory no distractor condition. It is a star, which means it is beyond 3 times the interquartile range. This is a probable outlier, so we will double check this condition with standardized values. Following up the probable outlier in the box plot, we converted this condition to absolute z-scores to see if it also registered as an outlier using this criterion. This case had a z-score of 4.1, which means we would consider it an extreme outlier. As we categorize the values, we can exclude this extreme outlier and use 29 participants as a final sample. As one of our IVs had 3 levels, we have to consider sphericity. Remember, if the IV only has 2 levels, sphericity does not apply, and it looks like the output for memory load. It will be blank without a p-value. However, we do have a value for distractor and the interaction. Distractor is statistically significant, suggesting sphericity has been violated for this factor. When we interpret the results, we would need to look at the sphericity corrected output for this factor, but the interaction looks fine. In the ANOVA output, we have the means for each condition. For example, the mean emission proportion for low working memory, high reward was 0.39, which means the participants looked at the distractor 39% of the time on average in this condition. Finally, we have the ANOVA output. There are 3 effects to report: the main effect of memory load, the main effect of distractor, and the interaction between memory load and distractor. All 3 effects are statistically significant, but we are going to focus on the interaction here. It's a relatively large effect, explaining 31% of the variance in emission trials looking at partial eta squared. The effects you focus on will depend on your hypotheses, so you can be selective if you have specific comparisons in mind, or examine all the significant effects if you're following more of an exploratory approach. When you have significant effects in a factorial ANOVA, you have different options. If the effect has 1 degree of freedom, like memory load, it's statistically equivalent to a t-test, so all you need to do is compare the marginal means for this factor. If you have 2 or more degrees of freedom in the main effect, you will need to conduct post hoc tests or apply your own t-test to follow up the pairwise comparisons. If there is a significant interaction, you will need to conduct simple effects analysis by editing the SPSS syntax or applying your own t-test. Just note, this doesn't apply when you have a 2x2 design. In this scenario, you just interpret the means as all 3 effects have 1 degree of freedom. To demonstrate the logic behind simple effects, consider a graph of the results. We have 3 lines, one for each level of distractor, and there are 2 levels on the x-axis, one for each level of memory load. The interactions suggest the pattern of means changes across the combination of each independent variable. Therefore, we need to break down the comparisons we are interested in. Here we're going to test the difference between high and low memory load for each distractor condition, meaning there will be 3 pairwise comparisons. Alternatively, we can compare distractor for each level of memory load. It's important that comparisons test your specific hypotheses, so consider which variable you are selecting as the moderator. In the following screencast, you'll see how to perform each type of simple effects analysis, either editing the SPSS syntax or conducting your own t-tests. Now that we know the interaction is significant, we can explore this using simple effects analysis. Click Analyze, General Linear Model, and Repeated Measures. The options should remain from before, but this time we need to click on EM means for estimated marginal means. Oddly, SPSS doesn't allow you to conduct simple effects analysis to break down the interaction using post hoc tests, but you can edit the underlying syntax to do it for you. Drag the interaction memory load by distractor to the right and click Continue. If you wanted the pairwise comparisons for the main effects, you could drag those over and tick Compare Main Effects. However, we need to edit the syntax. Click Paste, and the syntax window will open. These are the underlying commands that SPSS uses to conduct its tests. You can actually use SPSS just using syntax, but you would need to know how to code all the different tests, which I wouldn't recommend doing. But it is useful to save these commands, as you could rerun the syntax to receive the exact same options in output. We need to edit the line starting with EM means with the interaction in brackets. At the moment, this would just present you with a table of estimated marginal means, but we want SPSS to give us p-values for these comparisons too. Add compare with memory load in brackets. And at the end, add ADJ SIDAC. This is short for adjust SIDAC to add the SIDAC correction for multiple comparisons. It's very important the memory load name is exactly the same as you defined it when you first opened the repeated measures menu, and you could double check this with a name further up in the code. You could have also entered distractor in brackets, and this will conduct pairwise comparisons but the opposite way around. Click the large green arrow to run the analyses. Scroll down to the bottom of the output. All the other menus will be the same as the first time you ran the ANOVA, but now we have pairwise comparisons. You'll need to double check with the first table what the numbers mean for each level of the independent variable. An alternative approach that would give you the same answer is conducting your own paired samples t-tests. The only downside is you would need to add your own correction for multiple comparisons. Click Analyze, Compare Means, and Paired Samples t-test. We need to add 3 pairs to compare the difference between memory load for each level of distractor. Drag the high reward pairs to the first row, the low reward pairs to the second row, and the no reward pairs to the third row. Click OK to receive the output. We now have 3 paired samples t-tests, one for each pairwise comparison we want to focus on. We'll now break down the output for both of these methods to see how you can follow up a significant interaction. If you edit the syntax, we have each comparison of memory load for each level of distractor. Note the results are duplicated for each direction, so we only need the first row per distractor. For example, in the high reward condition, there were significantly more omissions in the high memory load condition than the low memory load condition. The benefit of using syntax is you can apply a correction for multiple comparisons. Here we applied the SIDAC correction. If you conduct your own t-tests, you would need to apply this yourself and change the alpha value. Alternatively, you could conduct your own paired samples t-test for each comparison of interest. You must select the pairs of variables you're interested in, for example, high reward for high and low working memory. If you compare the results to the previous output using syntax, you will see the mean differences in p-values are almost identical, but now you get the full t-test output to report. To report the results of your two-way within subjects ANOVA, you will need the f-value, the degrees of freedom, the p-value, and effect size for each ANOVA effect. If you have any significant effects, you will need to report the appropriate pairwise comparisons. For example, we could say there is a significant main effect of memory and distractor on the proportion of emissions. The greenhouse Geyser correction was used on the degrees of freedom for the distractor IV. There is also a significant interaction between memory and distractor. To follow up the significant interaction, we use simple effects analysis using the SIDAC correction. High reward distractors led to a greater proportion of emissions in the high memory load condition in comparison to the low condition. You would then outline the final two comparisons, which we omitted here for brevity.